Okay, so we've moved on to chapter 9 now, and we're going in more into depth into chemical bonding. So, if you recall from chapter 4, we talked a little bit about this, the different types of bonding. Actually, no, sorry, chapter 3. We have ionic bonding, where we had positive and negative ions come together, like in sodium chloride salt. So, the positive sodium ions are attracted to the negative chlorine, chloride, and ions, and there's a positive attraction between the unlike charges, and there's repulsion between the like charges. So it's all simple geometry. It'd be a very boring course if we studied all about ionic bonding. There wouldn't be very much to study. It's Pythagorean theorem and Coulomb's law repeated over and over again, and there would be some there would be some interesting things. You could be missing atoms here and there, like oh my gosh, I'm missing atoms. But that's about it. I mean, well, chemical reactions happen frequently on the surface, and metals too, where there are missing atoms on the surface and kinks in the surface. That's very common. But that's also well, that would be kind of fun. That would be kind of fun. But generally speaking, there would just be a lot of geometry. Metallic bonding, as far as metals are concerned, they're pretty easy. If you do the quantum mechanical simulations, do the supercomputers, you can see that looking at electrons like this diffuse gas, and it pretty much mirrors most of the properties of metals. There are some things that we don't understand. I mean, we're still learning more about different types of alloys and such. But I mean, as far as the properties of metals, having this really diffuse gas, sort of sea of electrons, as it's called, that's pretty much how it works, and it's described very, very well. I mean, do with a computer, it's not that hard. I mean, as far as quantum mechanical calculations, you do what's called the LDA, the local density approximation, and it pretty well defines it. Bulk metals are pretty easy. Look at the chemistry. It's when you have on the surface, when you have an interaction between atom and the surface, that's when it gets a little more difficult. But as far as straight metals, pretty simple. Now covalent bonding, this is much more difficult. So covalent bonding is by far the most difficult, and as such, we're going to spend a bit of time talking about it. And much of what I'm going to talk about these next two chapters, it's only part of the story. So really, the reason why things bond is it's lower energy. And we talked a little bit about this before. We've learned about atomic orbitals. When groups of atoms approach each other, and that's what a molecule is. The definition of a molecule is a stable group of atoms. So think about people, like a stable couple. What's a stable couple? They're always together, like, I love you, no, I love you more. Let's hold hands and be together and not be more than 3 inches apart ever. That's what a stable molecule is like. Okay, a stable molecule, they are together. They're next to each other. They move in unison. electron orbitals, molecular orbitals, and if they're low energy, they populate them. And the reason is because of the interaction between the electronic and magnetic field between the electrons with each other and the nuclei, the positive centers. And the math is crazy. We can do it. We can do it. But that's really advanced for this class. So we're going to start and we're going to talk about these rules and talk about what they mean, and they work, I mean, vast majority of the time. I mean, on the order of 99% of the time. It's not the whole story. The whole story, you can get that if you study more. You have to take lots of physics, lots of math, and I encourage you to do so. But we're going to start with these simple rules that we've known since the 1960s, and they work pretty well. So, and I mentioned the attraction. This is the Coulombic force. So we've mentioned this before. You have a constant 1/4 pi epsilon naught. Epsilon naught's permittivity of free space. Q1, Q2, that's the charge of one, charge of the second one, over the distance between the two squared. And this gives the force of attraction and repulsion. So we are going to visit ionic compounds again, although we're going to talk much more about covalent compounds. But let's talk a little bit about ionic compounds. So we have here sodium ions and chloride anions, and it's ripped apart and put back together. And so the energy that's released when these sodium ions and chloride anions get together, this is known as a lattice energy. So this is the energy that's released that. And remember we talked about thermodynamics and how things can be state functions. It doesn't matter what path you take. So one of the things that we can do with this, we can calculate or experimentally determine the lattice energy by looking at these steps. And this is known as the Born-Haber cycle for lattice energy. So Born-Haber cycle. Both very important people. Born and Haber, I should say Haber, the German guy, helped with ammonia synthesis. He's the guy who's a jerk. I don't know that much about Born, but Haber, he was a jerk. He invented chemical weapons. So bravo, Haber. Okay, so if you look at this figure here, the y-axis, so just this axis here, this is energy. So I should say specifically potential energy. So that's potential energy. So looking at potential energy, and here is the baseline right here. This is the baseline. This is solid sodium and gaseous chlorine. It takes energy. You can rip apart sodium to sodium vapor. That takes energy. Chlorine, Cl2 to Cl gas. That takes energy. And you can rip off an electron to form sodium ion. These are all exothermic. And then you can add an electron to chlorine to make chloride. This happens to be, I'm sorry, these are all endothermic. These here on the left, and the electron affinity of chlorine happens to be exothermic, so that releases energy. And we can also take sodium and chlorine and burn it. So let's put sodium and chlorine together and watch it react. So you can burn things in chlorine. You don't have to burn things in oxygen. You just need an oxidizer. So this burns and it forms sodium chloride. It's a very exothermic reaction. If we know all these things, this one we know 2, let's call it 6. If we know that all of these, we can determine what the lattice energy is via thermodynamics, the state function thing. So the delta H of the reaction, the overall reaction are these steps, and I've labeled them 1 through 5. So that's the Born-Haber cycle. So let's talk a little bit about lattice energies. So first thing here, bond lengths. So there's people are a lot like molecules. So how do you describe someone that you are really good friends with? You say, we are close friends. So what does that mean? That means when you meet, you are literally close together, right? You're a good friend. You're a close friend. Like, come on, man, you're my close friend. We need some love. Give me a big hug. Let's hug and let's be close together. So, what about people that you don't like? If you really like someone, so if you had to hear from me, a basic technique in flirting with someone is to be physically close to that person, right? If you like someone and they like you, or I'm sorry, he or she, not if you like someone and he or she likes you, you're close together. That is one way you can show that you enjoy each other's company, is to be in close proximity to each other. If you don't like someone and someone comes towards you, what do? You back away. You back away, right? You get distance. So the more bonded, more socially bonded you are to someone, the closer physically you are to that person. Generally speaking, atoms work the same way. So the closer the person, the proximity, the stronger the bond. And if you look here, so we have the halogens here. We have lithium, sodium, potassium, and cesium chloride. And lithium ion, so these are all +1, and lithium ion, it's a big molecule, it's a big ion in the size range, but it's a positive center. And if you look at lithium versus cesium, lithium's a tiny +1, cesium's a much bigger +1. So the attraction then, so the chloride doesn't change, so same size, and the chloride anion looks at the positive centers and it likes the smaller, more densely charged lithium ion, because the positive charge is more dense. There's more positive goodness in a smaller space, therefore the electron cloud is happier to be around lithium than it is cesium. And it shows this by the intermolecular distance. So 241 picometers versus 348 picometers. And we can compare that then to the lattice energy, and you can see that, in fact, the lattice energy is higher for lithium chloride than it is for cesium chloride, and it just decreases with size. Big surprise. The bigger the ion, the more diffuse the charge, the less attraction there is. So let's look at something else here, though. What about likeness to charge? So we have, or say similar distance, so we have sodium fluoride and calcium oxide. So just the intermolecular distances, they are very close. They are very close in size. This is just the size of the ions, and so electrons are negatively charged. You can't, they repel. You're trying to push them together. It's not like, even with someone you really like, you still like a distance, holding hands, gazing into each other's eyes. That's okay. Do you want to smush faces with them? You're like, oh, you're in my face. That's not fun, right? That's not fun, So there's still a happy distance between people. And if you look at sodium fluoride and calcium oxide, they're about the same size of ions, and so they have a certain distance that they like to sit with each other. And then if you look at the lattice energies between them, sodium fluoride is about negative 900 kilojoules per mole, and calcium oxide is about 3,400. Is this surprising? No, it's not. Because if you look at Coulomb's law, so right, this is Coulomb's law, charge of 1, charge of second over distance squared, right? So let's look at this one. So sodium +1, fluorine -1, and then compare it to +2, -2. So +2, -2, that's 4. So if you look at the so 900 versus, so 9 times 4 is 36. So more or less, calcium oxide is about 4 times as strong as sodium fluoride. Is that surprising? No, because of Coulomb's law. That's just the multiplication of the charge. You double the charge, you increase it by a factor of 4. So not that surprising. Okay, so let us arrange these ions in increasing magnitude of lattice energy. Low to high, so we're going low to high. We have calcium oxide potassium bromide, potassium chloride, strontium oxide. So, and the order of importance, the charge is more important than the size. So, the bigger the atom, the smaller the lattice energy, or the smaller the ion slash atom, the stronger the attraction, and the bigger the charge, the stronger the attraction. So, calcium is +2, oxide is -2. Potassium is -1, bromine is +1, plus minus, strontium +2, -2. Okay, so the +2 -2s are going to be stronger. They're much, and you can see this trend here that the charge is much more powerful than the size when it comes to in the strength of the bond. So the lower one is going to be the +1 -1. So which one's lowest energy? So bromine is beneath chlorine. So here's the periodic table, right? So bromine is bigger than chlorine. So bromine is the biggest one. So the weakest one is going to be KBr, and then that's going to be less than KCl. So now it's between the +2 and -2. Oxide's the same, so that's not going to be the problem. We have calcium and strontium. Here is calcium, here is strontium. Strontium's bigger, so that's going to be less than strontium oxide, and then calcium oxide's the biggest. So low to high. That's the order of the relative lattice energies. So you can pause this if you want to try and figure this on your own. What is the highest lattice energy? And I told you the charge is the highest, so if you look at the charges, this is plus minus. Vanadium oxide, this is going to be +3 -2. Tungsten carbide, +4 -4, +1 3 minus. And so from all of these, it's just plain old magnitude. It's the tungsten carbide has the highest energy here. Okay, so let's talk about ionic compounds and what they're used for. So silver nitrate, this is a very good antibacterial agent. So, and they put it in some Band-Aids. Problem with it, especially with my fair skin, it turns skin brown. Okay, so one thing about silver nitrate, I mean, if you already have a brown complexion, for me, if I put it on, it turns brown on me, and that's true for pretty much every single pale-skinned person like me. And so we use it for antibacterial properties. Barium sulfate, contrast imaging for X-rays. I've had a CT scan, and I did it on my gut, and they gave me that stuff to drink, and it tastes terrible. Ugh. But it's, I mean, barium tends to be pretty toxic. Barium sulfate is completely safe. It's very insoluble. So anyway, so calcium sulfate, this is used to make plaster casts. I've used this in art class. I took an art class at UH Manoa. Loads of fun. It was on bronze casting. I used my tuition waiver. We did the lost wax method, and we made plaster casts, and that was a lot of fun. So if you get a chance to do that, if you want to do some metalworking, that's a wonderful class, and you can take. We don't really use it to make plaster casting. We use fiberglass for casts, or not even so. We use plastic and air, right? Or even a brace, right? So we plaster cast. That's old school. Okay, potassium permanganate. So you can use it to purify water. It's a purple stuff. It's really reactive. Very good reducing agent. And for extreme cases, used to treat trench foot. So it's a good trench foot if you have your boots in the mud for months and your feet start to rot, you can put potassium permanganate on it. That's a good treatment for that. Of course, there's very few cases where that happens these days. Potassium ion antiseptic. This is used to prevent radiation sickness, very specific type. So our thyroid gland here, it is an organ it's part of your endocrine system. It releases a hormone called thyroxine, which it gives your metabolism. That's like your idle. Like if you turn on a car, right? You turn on a car and your idle, like it's if you let the car sit there, the chug of the car, that's the idle of the car. That's what thyroxine does for humans. That's your idle. And of course, if you imagine if you turn on your car and your car engine is like all the time, that's like having a high metabolism. So that's why people that have high metabolism, they're always skinny because they're running hot all the time. And there's also conditions with your thyroid where you can run too hot, specifically certain disorders with that. Okay, so what? Well, your iodine is used in your thyroid, and whenever you take iodine, your body says, "Oh, I know what to do this. Give it to your thyroid." The thyroid knows what to do with it. So, if there's a nuclear event, a nuclear meltdown at a power plant, an atomic bomb going off, one of the common byproducts is iodine 131. So iodine 131 has a half-life of about 8 days. And the issue is if you have iodine, and you can breathe it in through the air. And if you breathe it in and it goes to your thyroid can get hit with a really high dose of radiation. What happens after a nuclear event, like so what happened after the Fukushima event or after an atomic bomb goes off, if you give people potassium iodide, then your thyroid gets saturated with iodine and then it can't take up anymore, and that prevents that specific type of radiation sickness. I mean, you can't just take potassium iodine and then get hit by a nuclear bomb like, oh, I'm fine. No, it prevents a specific type of radiation sickness. So you're like, well, I'll just take potassium iodide all the time, and just in case a nuclear bomb goes off. That's a bad idea too. You can get a condition called iodism from too much iodine. So it's one of those risks versus rewards things. So taking too much iodine is a bad idea. But if there's an atomic bomb, the risks of iodism is better than having long-term cancer and or damage to your thyroid from the radiation. At the same time, people that have treatment for things like Hashimoto's or Graves' disease with their thyroid, people have to go on an iodine-free diet. So one of the things about the United States of America, we enrich our food. We put B vitamins in everything, and we put iodine in our salt. So because of that, if you are eating processed food, so things like milk that you get from the store, soda from soda fountains, those have iodine. They use it to clean out the lines. If you have anything but sea salt or even sea salt's got some iodine in it. Like kosher salt doesn't have iodine in it. If you have that, your thyroid's pretty good in terms of if you eat lots of seafood. So fish has a good fair amount of iodine in it. You're fine. Don't have to supplement it too much. So that's one of the issues if someone is actually trying to use radiation to kill his or her thyroid. That person has to go on an iodine-free diet, which means you eat meat and fruit, basically. That's all you can eat. You can't really eat any processed food. It's pretty hard to do. Okay, so going on lithium carbonate. This used to treat a very specific type of bipolar disorder. We've noticed that over time, there's better drugs now, but it kind of levels people out. Manic disorder is you have these short periods of high and these kind of long periods of lows, followed by short periods of high. This tends to stabilize people that have that specific type of bipolar. And there's a song by Nirvana called Lithium, as a matter of fact. Magnesium sulfate, so a specific issue is pregnancy that from elevated blood pressure, although in general, all magnesium salts tend to be laxative. So magnesium sulfate is also a laxative. I've used it to soak my feet. So like if I get a splinter or something like that, and I can soak my feet in magnesium sulfate solution, not the salt itself, also known as Epsom salt. Epsom salts. Magnesium hydroxide, this is Rolaids. If you take Rolaids, that's a primary ingredient in Rolaids. It's an acid and laxative. So all magnesium salts are laxatives. Sodium bicarbonate, they used to use this to treat heartburn, but they tend not to anymore because of the sodium. You can use it for toothpaste. So I actually do brush my teeth with sodium bicarbonate. I take a little bit of about a pea-sized amount of fluoride toothpaste, and then I put sodium bicarbonate on there, baking soda. I just sprinkle it on with a spoon, and I use that to brush my teeth. So the reason why I do that is because of the microclimate of your mouth, the bacteria that prefers the alkaline, the basic part. So sodium bicarbonate is alkaline. It's a basic salt. That the Having that kind of microclimate in your mouth is beneficial for gum health. So also, for people that have acidosis, if you have acidosis and it's really bad, you can go to the hospital and they'll inject you with a magnesium bicarbonate solution. That'll bring your pH up a bit, so to keep the acidosis from killing you. Uh, so. Sodium fluoride, used to strengthen teeth. So fluoride's a great thing. Here in Hawaii, we do not put fluoride in the drinking water, and also we have the highest, or at least one of the highest incidence of cavities in all of the United States. And what does fluoride do? Fluoride, well, I guess the military bases, if you're in a military base, they fluorinate the water there. They don't fluorinate the water anywhere else in the state, at least the non-military base areas. What this does, so there's the mineral on the skin of your teeth. The mineral, your enamel, is a mineral called hydroxyapatite. It's a calcium phosphate hydroxide mixture. What fluoride does is it replaces the hydroxide and the hydroxyapatite, and that makes the mineral harder. It also makes it less soluble. Fluoride also is antibacterial, so it kills bacteria. So it hardens and strengthens your teeth and kills bacteria. So in a small amount, it's okay. It's pretty good. In large amounts, it can cause other issues. So, but moving on, zinc oxide, you can use this as a sunscreen. I like the organic kind, organic meaning carbon containing, not like the hippie organic stuff. I just prefer that. I use lots of sunscreen. I don't like zinc oxide. Titanium dioxide is also used for that. It just clogs my pores. And so I just get these white dots in my big pores, and then I have all this white gunk in my pores from it. I just prefer to use the organic sunscreen with that because it just works better on my skin. But some people love it, so all the mineral sunscreens, that's the mineral sunscreen, the zinc oxide. Okay, so we've mentioned valence electrons last chapter, and here's fluorine. Fluorine has 7 valence, and two fluorine atoms can come together, and what they can say is, you know what, I've got 7 electrons, you've got 7 electrons, what if we keep 6, but we share 2? That way we both can have 8 electrons, and we're just like a noble gas, we're just like neon. We're like neon in disguise. So that's what fluorine does. It comes together and it shares 2 electrons, and we indicate this with a line. So a line says we're sharing 2 electrons. And same thing with oxygen. 2 oxygen goes together. They both have 6 outer electrons, 6 valence. So you know what? Let's keep 4 and share 4. And that way we'll both have 8. So what I mean by that is, let me cover up this oxygen atom. So you know what, like, let's cover up this. Haha, I have 8 electrons now. You're like, haha, I have 8 electrons now. So each oxygen atom has 8 electrons. Same thing with the nitrogen. Nitrogen will share 6. One has 8. The other one has 8. Looking at that. So let me get my pen back. And each 2 electrons shared we indicate with a line. So this is Lewis' theory. So remember, Lewis thought that atoms were boxes, or like boxes, but wrong. Okay, and I mentioned this briefly about electronegativity. So this here, it's kind of a periodic trend, but this atom right here, that's fluorine. So fluorine is the most electronegative, and generally speaking, this is the positive way, this is the positive way. You can see there's some weird things, like there's this island here. So, what is electronegativity? Electronegativity is the ability of an atom to draw electron density to itself, and this deals with bonding atoms. So, when atoms bond, ionic or covalent, electron density is so electrons are not like dots. So, fluorine, this is not that doesn't describe the electrons. Okay, electrons are fuzzy sort of particles that are in many different places at once. And so if you have a molecule, the electrons kind of hang around the fluorine quite a bit and then a little bit with the hydrogen, but they're where's the electron? It's in both places. It's in many different places at once and it flows everywhere. So that's really what happens with electrons. That's the truth of the matter. But we like to make it simple, so we do this. Or even simply, we just say one line here. And we I mean, if people want to look into it and understand that they're really, electrons flow and that kind of thing. So, okay, so fluorine is the most electronegative, which means it's like an electron vacuum cleaner. It just draws electron density to itself. So, if you ever go out and you see like a really attractive person out and about, like if you go out on a street party or somewhere on the beach, someone who is really attractive, there tends to be a following around that person, right? So that person tends to draw other people to himself or herself. And the same thing is true for atoms. There are some atoms that are outright attractive. So fluorine, this is the supermodel. This is the electrons look at that person, that atom, like, I want to be by that plus center, that tiny atom with that +7 center. I am so attracted and drawn to it. And then they look at cesium, you're like, that's a very big atom with a very weak charge. I'm just not attracted to that. I can't have my negative self be attracted to that just really tiny positive charge. So I'll give you a little bit of my time. But fluorine walks by, oh man, I'm just drawn to that +7 charge. So that's what electrons feel. Electrons are very indiscriminate when it comes to that. They like the big charges in tiny spaces. Okay, so now this is if you've ever, like when I say slept, I mean shared a bed with someone. If you've ever shared a bed with someone, maybe you've noticed someone's a blanket hog. Maybe you're the blanket hog. I don't know. Well, maybe you've noticed that for bedfellows, if they're good bedfellows, they share the blankets equally. And if you're somewhere cold like Alaska in the winter, you want to have those blankets over you. But some people, they rip the blankets away. So here is showing hydrogen chloride, or I should say hydrochloric acid, it's in water. Chlorine is more electronegative, has a +7 center, and hydrogen is +1. And chlorine is electronegative. It's very electronegative. It draws electron density to itself. So what happens is that the chlorine draws electron density away from the hydrogen, and it forms what's called a polar bond. So the polar bond, where you have a positive end and a negative end on the hydrogen chloride. So the electron density, the electrons are drawn towards the chlorine. So that means the electron density, so remember electrons are kind of fuzzy, it is just drawn towards the chlorine rather than the hydrogen. There's still electron density around hydrogen, but there's more around chlorine. And that's known as a polar covalent bond. And here is this chart here. This is something I disagree with. So the electronegativity distance 0 to 4, it's called a covalent bond. And the reason for this is organic chemists. If you talk to an organic chemist, the organic chemist will tell you that hydrogen and carbon have a completely covalent bond. That's not true. Carbon is more electronegative. The electron density goes towards carbon in a hydrogen-carbon bond. It's a small difference, but it's still hydrogen adds more electron density to the bonding scheme. So I'm a physical chemist, so I think of electrons as fuzzy clouds. The organic chemists, they think more in terms of reactions and where oxidation happens and that kind of thing. So just different type of chemist. So in my opinion, it's wrong. But I'm a physical chemist, so of course I think it's wrong. But for you going on, if you take organic chemistry, listen to your teacher and completely agree with him or her saying, oh, absolutely, hydrogen-carbon is a completely covalent bond. So if you talk to me like, oh, I can't believe that stuff. Organic chemists, who likes carbon anyways? Okay, so small difference, it's a covalent bond, but so if it's the same atom, um, it's going to be a covalent bond. You can have a polar molecule even if it's the same atom. Ozone is a polar molecule. We'll talk about polar molecules later. But the bonding will be covalent. It will be shared evenly between the atoms. So intermediate polar covalent, if it's a very large difference, ionic. Well, the ionic bond, it's more or less the electron is ripped off of one atom and given to the other. Is that entirely true? No. The electrons can still flow. You can still get electron density around the positive cation from the negative anion. That can happen. But it's just not as much. And we pretty much say like, oh, you know what? It's just not even there. So, but the truth of the matter is, it can be. But generally speaking, though, we just kind of ignore that and say it's not. So, and there's a continuum of bond types. Okay, so we will go on to the second part of this chapter.